2026 A-Level Physics Paper 1, questions 31 up to 40. If you are interested in any of the other questions from question 1 up to question 30 or question 41 up to question 50, then check out the links in the description down below. Now moving on to the first question, question 31 says, a calorimeter of heat capacity 50 joule per Kelvin contains a liquid of mass 0.25 kilograms. A 10-watt immersion heater is placed into the liquid, the immersion heater is switched on, and after some time, the temperature of the liquid reaches a steady value. Now when this happens, they say, the heater is now switched off and it is observed that the initial rate of fall of temperature of the liquid is equal to 1.0 times 10 to the minus 2 kelvins per second. Now given this, they ask us, what is the specific heat capacity of the liquid? Now for this, I'm going to label the specific heat capacity as C sub L. So simple C sub L to indicate it is the heat capacity per unit mass of the liquid. Now considering the situation, we can see we have a calorimeter of heat capacity capital C of 50 joule per Kelvin. I'm going to call it capital C sub C to indicate that the calorimeter's heat capacity. Now inside the calorimeter, we have liquid of mass 0.25 kilograms, and therefore the heat capacity capital C sub L is equal to the mass of 0.25 kilograms times simple C sub L. Now given this, they say we have a heater placed into here and the heater outputs 10 watts of power into the liquid and heats up the liquid. So from the heater, the liquid gains 10 watts of power or 10 joules per second of energy into the system. Now as the liquid heats up, it will eventually reach a steady temperature, and the reason is that as it heats up, some heat will start to escape from the liquid outward from the calorimeter, and at a certain point, the amount of heat escaping per second will be exactly equal to the amount of heat added per second by the heater. So the heat escaping will also be equal to 10 joule per second at that point. Now at that point, when we remove the heater, we can see while this energy input is removed, the energy output at that particular temperature will still be 10 joule per second out of the liquid. Now due to this, the amount of energy lost per second in the liquid is 10 joules per second or 10 watts. Now considering that, as the liquid cools down, we can say amount of energy lost, Q, is equal to MC theta, or if we have the general heat capacity capital C, we can write this as being equal to capital C times theta. Now in this case, you can see capital C is going to be equal to capital C sub C plus capital C sub L, and therefore it's equal to 50 plus 0.25 times C sub L, and that times theta is the amount of heat lost. Now if you consider the rate of heat lost, it's equal to this divided by time. So Q divided by T is equal to this times theta divided by time. Now here we are given theta divided by time, the rate of temperature loss is equal to 1.0 times 10 to the minus 2 kelvins per second. So therefore, instead of this value, I can substitute in 1 times 10 to the minus 2 or 10 to the minus 2 kelvins per second. So therefore, this is the expression for the heat lost per second. Now if that value is equal to 10 watts, we can say 10 is equal to 50 plus 0.25 times C sub L times 10 to the minus 2. Now solving this, we can see if we take the 10 to the minus 2, the other side becomes 10 to the plus 2, which is 100, and 100 times 10 to the 1000, so we get 1000 equals 50 plus 0.25 times C sub L. Now here, if you subtract the 50, we get 950 equals 0.25 or 1 over 4 times CL, or CL over 4, and therefore CL equals 950 times 4, which is equal to 3800. So therefore, the answer must be 3800. Now since we used SI units, the answer here is going to be 3800 joules per kilogram per Kelvin. So therefore, the answer here is answer number 3, 3800 joules per kilogram per Kelvin. Now moving on to question 32. Question 32 says, figure 1 shows a child pulling himself upward at a constant speed while standing on a movable platform that is hung on a frictionless pulley. So here we can see this child is moving upward at a constant speed by pulling this rope downward at a different constant speed. Now figure 2 shows the child on the platform being pulled upward at a constant speed by another child that is standing on the ground. So in this case we can see this child is being moved upward at a constant speed by a force in the rope, and the same force in the rope is being applied onto the second child. However, since the second child is not moving upward, we have to conclude that this child must be heavier than the first child, and therefore the force being applied upward on the child is not enough to lift the child up. So anyway, the question then says, assume that the ropes are massless and inextensible, and given that, consider the following statements. Now statement A says, the force applied by the child in figure 1 is half of the force that's applied by the child on the ground in figure 2. Statement B says, to move up by the same height, the work done by the child in figure 1 is less than the work done by the child on the ground in figure 2. And statement C says, the reaction forces from the platform acting on the child standing on the platform are equal in both of these situations. Now to answer this, let's consider the first statement. And for the first statement, let's write down the tensions in ropes 1 and 2. So I'll call this tensions T1 and I'll call this tension T2. Now considering this, let's also mark the weight of the child. So the weight of the child is going to be mg in the downward direction. So we have mg downward here, and considering this we can see, in the first situation, since the child is moving upward at a constant speed, acceleration is 0. We can also see the tension T1 here is acting on the box, which is acting on the child, and tension T1 here is also acting on the child, since the child is holding the rope and pulling it downward. So therefore, both of these T1s are acting on the child, and therefore, by equilibrium, mg must be equal to T1 plus T1 or 2T1. Now in the second situation, we can see only this single T2 is acting on the box that's holding the child, and therefore, by equilibrium, since this child is also moving upward at a constant speed, we must have T2 being equal to mg, and we can write therefore mg equals T2. Now from this we can see, if mg is equal to 2T1 and mg is also equal to T2, then 2T1 must be equal to T2. Now considering this we can see, if T1 is the force that's on the rope and T2 is the force that's on the other rope, then T2 is double the value of T1. Now if the child is applying this force and the other child here is applying the force T2, then we can see the force applied by the first child, which is T1, is equal to half of the force that's applied by the second child, which is T2. So therefore, the force applied by the child in figure 1 is in fact equal to half of the force that's applied by the child on the ground in figure 2. So A is correct. Now moving on to B, B says, to move up by the same height, the work done by the child in figure 1 is less than the work done by the child on the ground in figure 2. Now this statement is wrong, because if you consider moving up by height h, both of these children will have to apply a total work done of mgh. Potential energy must be conserved as we move up. So therefore, the energy expelled by both of these ones, as in the work done, must be equal in moving up by the same height h. Now even though that's the case, you might doubt it, because this child has to apply half of the force of T1 to move himself upward, but this child has to apply a force of T2, which is double of T1, to move this child upward. Now while that is true, you might be forgetting one thing. So in the second situation, in order to move up by a height h, like so, this child here has to pull this rope downward by a length h. So this has to move downward by the same length h. However, in the first situation, to move up by a height h like this, this child has to pull this rope downward by a total height of 2h. The reason is, if you want to move upward by h, then on this side of the pulley, this length of rope has to decrease by a height h. But if that happens on the other side, this side also would have to decrease by a height h. So therefore, the overall length of the rope at this point, from this point onward, must decrease by a total length of 2 times h. To decrease like that, the child here must pull this rope downward by that total length of 2h. So therefore, for this child, to move his rope upward by a total, or move his box upward by total height h, he has to pull the rope downward by a length of 2h. Now according to that, if work done is equal to force and distance, then for this child, the force is equal to T1, but the distance is equal to 2 times h. For the other child, his force is T2 and his side is only h. Since to move h upward like this, he has to pull by only h downward like this. So therefore for him, the work done is simply equal to T2 times h, but here, since T2 is equal to 2T1, his work done is also equal to 2T1h. So both of them do the same amount of work of 2T1h, and therefore B is incorrect. Both of them do the same amount of work. Now moving on to statement C. Statement C says, the reaction forces from the platform that are acting on the child standing on the platform are equal in both situations. Now in this situation, the child is having a force upward on him of mg to prevent himself from accelerating downward. So here, the reaction force upward is mg. However, in the first situation, if we consider reaction force of r here, and consider the other tension here of T1 that is acting on the child's hands, since these two forces of T1 and the r here are counteracting the downward mg, we can conclude that r must be equal to mg minus T1. So therefore, r is not equal to mg like it is in the second situation, and therefore the two reactions here are not equal to each other. So statement C is also wrong. So that means A is correct, B is wrong and C is wrong, and therefore only A is true. So the correct answer is answer number 1. Next, if you consider question 33, question 33 says, a star system consists of 3 collinear stars of equal mass m. The 2 companion stars move around the central star in a circular orbit of radius r. Given this, they ask us, what is the linear speed of a companion star relative to the central star? Now what they're talking about here is 3 collinear stars or 3 stars in a straight line like this. Now out of these 3 stars, the central star doesn't move, but the other stars rotate in a circular orbit around the central star like this. So these 2 companion stars rotate about the central star like this. Now naturally, it is very unlikely to find this kind of star system in nature. The reason is because of the 3-body problem. The 3-body problem states that if you have 3 bodies, if they are not perfectly stable, then as they orbit each other, one of the bodies will become unstable, and therefore either one of them will shoot out into infinity, or 2 of these bodies will collide with each other. Now in this case, let's assume that this star system is perfectly stable, and therefore if the tangential velocity here is v, the tangential velocity on this side is also v, and when these stars orbit, their orbits are perfectly circular, and therefore the centripetal force on this star, which is going to be m v squared divided by r, is equal to the force of gravity applied by this star and this star on this companion star. Now considering that, if we consider the force of gravity here, force of gravity, if we substitute gm1 m2 divided by r squared, for the central star, the radius here is r and the mass is capital M, and therefore we will get g times capital M divided by r squared. Now to that we have to add the gravitational force from the second star. The second companion star is a distance of 2r and has a mass of capital M, and therefore the force from this star is g times capital M divided by 2r whole thing squared. Now simplifying, we can see from this equation we will get mv squared divided by r being equal to g mm divided by r squared plus gmm divided by 2r whole thing squared, which is 4 times r squared. Now simplifying, we can see if we multiply the top and bottom here by 4, we can get a common denominator of 4r squared and get 4gmm divided by 4r squared plus gmm divided by 4r squared being equal to mv squared divided by r. Now here, if we divide everything by capital M and also cancel one of the r's, we can see we'll get the equation v squared equals 4gm divided by 4r plus gm divided by 4r, or 5gm divided by 4r. Now taking the square root of both sides, we can see we'll get v equals square root of 5gm divided by square root of 4 times r, which is going to be 2 times the square root of r. So therefore it will be equal to square root of 5 divided by 2 times the square root of gm over r. So this is equal to the tangential velocity of one of these stars. Now since the central star here is stationary, we can conclude that the tangential velocity here is equal to the velocity of the companion star relative to the central star. Therefore, the linear speed of the companion star relative to the central star is equal to root 5 over 2 times the square root of gm over r, which is equal to answer number 5. Now moving on to question 34, it says a thin conducting plate is pulled out horizontally across a uniform magnetic field that is acting vertically downwards as shown in the figure. Now given this, they ask us which of the following diagrams accurately represents the direction of the eddy currents that are induced in the plate. Now for this question, what we will do is to apply Fleming's right-hand law of electromagnetic induction. It says that if you have a conductor that travels through a magnetic field and you take your right hand like this and align your thumb with the direction of motion of the conductor and align your index finger with the direction of the magnetic field, then your middle finger will automatically show you the direction of the induced current inside of that conductor. Now according to that, if we go up and take a look at a magnet, we can see the magnetic field is going from north to south, which is in the downward direction like this, and our plate is moving horizontal like this. Now according to these two, if you take your right hand, take your thumb and align it in this direction, and take your index finger and align it in the downward direction, you can see the current resultant is going to be in this direction right here. So therefore, in each of our plates, we have to check if the current in the middle, right below the magnetic field, is in this direction or not. Now immediately we can see number 1 is the correct answer, since the eddy currents are traveling in this direction like this. So number 1 is correct. Now looking at the other ones, we can see in number 2, the eddy currents are traveling in the opposite direction that is indicated, and therefore it is incorrect. Now in number 3, one of the eddy currents is traveling in the correct direction like this, but the other eddy current is traveling the inverse direction like this, and therefore it's wrong. The same thing is there with number 4. Number 4, this one's traveling in the wrong direction, but this eddy current is traveling in the correct direction. In number 5, there's even more wrong things, because in number 5, one of the eddy currents here is traveling in this direction, while the same eddy current on the other side is traveling the opposite direction. So here there's even more things wrong. This is going this way, this is going the other way, and over here, this is going the wrong way, this is going the correct way, this is going the wrong way. So multiple things are wrong in number 5. In the other one, some things are wrong, and the correct one is answer number 1. Next, if you consider question 35, it says, two parallel wires of infinite length carry equal currents along the same direction into the plane of the page. Given this, they ask us which of the following diagrams best represent the pattern of the resulting magnetic field lines. Now to solve this one, we know the right hand corkscrew rule, aka the right hand grip rule. This rule says that if you have conventional current I flowing through a wire and you take your right hand and grip the wire such that your thumb is pointing in the direction of the current, then your fingers will curl in the direction of the magnetic field. So here we can see our thumb is pointing upward, and when that happens, the fingers will curl around the wire in the direction of the magnetic field, which is curling in this case around like this. Now in the question, we are told that we have infinite length wires that are carrying currents in the same direction into the plane of the page. So we have to consider wires that are going with currents into the page like this. Now to consider that, let's take our hand and take our thumbs, point them inward into the page, curl our fingers and look at the direction. Now if you do that, you will see your fingers curl clockwise around the X, and therefore the magnetic fields will be curling clockwise like this around the wire. Now in the question, we have not one wire but two parallel wires of infinite length carrying equal currents in the same direction. So therefore, instead of considering just one wire, we have to consider two wires right next to each other, both carrying current into the page, and consider the magnetic fields. So around the wires, it will be clockwise on both of them, but if you consider the middle of them, you will see from one wire, if you consider only that wire, there will be a magnetic field like this, and from the other wire, if you consider only that wire, there will be a magnetic field like this. Now these two magnetic fields cannot possibly both go through the same exact point, because that would mean that magnetic flux lines will intersect each other, which is impossible. Now due to this, what's actually happening here is that these two magnetic field lines will cancel each other out, leading to there being no magnetic flux in between these two wires. So therefore, in the space in between these two wires, we should expect a null point where there are no magnetic fields. Now looking at the answers, we can see answer 2, answer 4 and answer 5 are wrong, since they all have magnetic fields in the middle of the two wires. Now other than them, we have answer 1 and answer 3. Now looking at these two, we can see if these were the position of the two wires in the first answer, around this wire we have clockwise magnetic field, and around this wire also we have clockwise magnetic field. So this could be the correct answer. Now looking at the other one, we can see around the wires we have anticlockwise here and anticlockwise here, which is wrong. And therefore answer 3 is wrong, and the correct answer is answer number 1. Magnetic field around the wires in the clockwise direction, null point in the middle, and around them also we will end up having a clockwise magnetic field. So with that, we're done with question number 35. Now moving on to question 36, it says a heavy uniform rod of mass capital M and length capital L is suspended from rigid ceiling by two vertical wires that are attached to each end of the rod. They then say the unstretched length and the cross-sectional area of the wires are given to be L and A respectively. They also say one wire is made of copper while the other wire is made of brass, and they mention that the Young's moduli of copper and brass are E sub C and E sub B respectively, where E sub C is given to be a bigger number than E sub B. Now given this, they ask us what is the angle theta in radians shown in the figure that the rod makes with the horizontal. So what is this angle right here? And for this they give us a hint by saying for small angle theta measured in radians, sine of theta is approximately to theta. Now if you look at the diagram, you can see since we have downward weight of mg and these two wires are holding up the weight, both of these wires have certain tension in them. Now since this rod is uniform, this weight is going to be in the center of the rod, and therefore since in the center both of these wires will be holding the same weight of mg over 2. So this wire has a tension of mg over 2, and this one also has a tension of mg over 2. Now due to this, both of these wires will be extended past their natural length. So if the natural length is L, then both of these wires will be extended past L, and each of them will have a certain extension. Let's call this extension right here E1 and the other extension here E2. Now if this is E1 and this is E2, we can see the height in this triangle right here is equal to E2 minus E1. So whichever one is stretching more, that one's extension is E2, and we have E2 minus E1 being equal to the height of the triangle. Now given this, in order to find E2 and E1, what we can do is to apply the Young's modulus equation. It says that the Young's modulus E is equal to stress divided by strain, where the stress is equal to the force per unit cross-sectional area and strain is equal to extension per unit natural length. Now rearranging, we can see we can get E equals F times L divided by E times A. And rearranging, if we make extension subject, we can see we get E equals F times L divided by capital E times A. So we get extension equals force times natural length divided by Young's modulus times cross-sectional area. Now considering each of these, we can see for the copper, E is equal to E sub C, and for the brass, E is equal to E sub B. Now for those two, if we consider their forces and considering their extensions, we'll get the equations extension of C, extension of copper, being equal to force of mg over 2 times natural length of L divided by Young's modulus of E sub C times cross-sectional area A. And for E sub B, we'll get E sub B being equal to mg over 2 times L divided by, in this time, we'll have E sub B times A. So we get these two equations for the two extensions. Now in this case, we can see since E sub C is bigger than E sub B and extension is inversely proportional to E, we can see the extension of the brass will be bigger than the extension of copper. So E sub B is bigger than E sub C. Now from this we can see, since this wire extends more, E sub 2 should be equal to E sub B. So therefore, the little height here, E2 minus E1, is equal to E sub B minus E sub C. Now considering that, if we substitute the two equations, we can see E sub C minus E sub B, or rather E sub B minus E sub C, E sub B minus E sub C is equal to mg times L divided by 2 times A times 1 over E sub B minus mgl divided by 2A times 1 over E sub C. So we can see we get mg times L divided by 2A times 1 over E sub B minus 1 over E sub c. So this is the equation for the little height in this triangle right here. Now considering sine of theta, we can see sine theta is equal to opposite divided by hypotenuse, or this little height divided by capital L. And therefore, we can get sine theta being equal to this whole thing divided by capital L. So if we substitute that in, we can see sine theta is equal to mgl divided by 2a times 1 over E sub b minus E sub c divided by capital L. Now using the hint they gave us, we can see, since for a small angle, sine theta is approximately equal to theta, we can also say theta is approximately equal to this value. And therefore, theta is approximately equal to mgl divided by 2a divided by L, or divided by 2al times 1 over E sub b minus 1 over E sub c. So therefore, this equation right here is the answer for theta. Now going up, we can see out of our answers, the one that matches this is answer number 2. Answer number 2 matches the form of mgl divided by 2a capital L times 1 over E sub b minus 1 over E sub c. So therefore, the answer here is answer number 2. Next, if we consider question 37, it says a circuit with an ideal diode in series with a resistance R is shown in the figure 1. A supply voltage in the form of a square wave with amplitude V0 is applied between the terminals A and B as shown in the figure 2. Now given this, they ask us what is the value of the average power dissipated across the resistance R over one cycle. Now looking at the diagrams, we can see our square wave alternates between positive V0 and negative V0 volts. So considering that, we can see, since this diode will only allow current to flow in one direction, either the top half or the bottom half of our supply voltage here will be cut off by the diode. So therefore, the resistance R here will only have either this top half or this bottom half of the cycle flowing through it. Now considering that, we can see power is only flowing through the resistance half of the time. And in that half of the time, we can see the voltage is V0 and the resistance is R. Now power is equal to voltage times current, or alternatively, if we substitute using V equals IR, we can get I squared times R or V squared divided by R. And in this case, we're going to be using this one. So in this one, we can see if we had a constant power, the power would be equal to V0 squared divided by R. However, since the power is only on half of the time, the average power is equal to 1/2 of that value, or 1/2 times V0 squared divided by R, or V0 squared divided by 2R. And therefore the answer here is V0 squared divided by 2R, or answer number 3. Now moving on to the next one, question 38 says, a uniform wire of diameter 1 mm is bent to form a circular loop as shown in the figure. The radius of the loop is going to be 10 centimeters and the resistivity of the material of the wire is going to be 3.0 times 10 to the minus 4 ohm meters. Now they then say, two conducting wires are connected at points A and B on the loop such that the point B can be slid around the loop freely like so. Now given this, they ask us what is the maximum resistance that can exist between the points A and B. Now for this one, if we look at A and B, we can see we have two wires in between A and B, and therefore there are two resistors in between A and B like this. Now these two resistors here are parallel to each other, and therefore in order to find the resistance between A and B, we have to find each of these resistors individually. Now here, I'm going to call the shorter wire segment here as AB1 and the longer wire segment as AB2. So here we can see, if we have these two wires being AB1 and AB2, then the total length of AB1 plus AB2 is equal to the circumference of this circle. Now the radius is equal to 10, and therefore the circumference is equal to 2 pi r, or 2 pi times 10 centimeters, or equal to 20 pi centimeters. Now therefore, if I say the length of AB1 is equal to x centimeters, then AB2 will be equal to 20 pi minus x centimeters. Now to find the resistances of these two wires, what we have to do is use the formula R equals rho L divided by A, where R is resistance, rho is resistivity, L is length, and A is cross-sectional area. So here for RAB1 and RAB2, for RAB1, we'll have resistance of AB1 being equal to rho, which for now I'll leave as rho, times the length, which is equal to x centimeters, or x times 10 to the minus 2 meters, since we have to use SI units, divided by a, which for now I'm not going to substitute, I'm going to leave as is. Now similarly, for RAB2, we'll have rho times the length of 20 pi minus x centimeters, or 20 pi minus x times 10 to the minus 2 meters, and that's divided by a. Now here, since the two resistors RAB1 and RAB2 are parallel to each other, we can say 1 over R, where R is the total resistance, is equal to 1 over RAB1 plus 1 over RAB2. Now taking these under a common denominator, we can see we'll get RAB1 plus RAB2 divided by RAB1 times RAB2. Now substituting in, we can see we'll get for RAB1 rho times x times 10 to the minus 2 divided by a plus RAB2, which is rho times 20 pi minus x times 10 to the minus 2 divided by a, divided by these two multiplied together. So rho times x times 10 to the minus 2 times rho times 20 pi minus x times 10 to the minus 2 divided by a times a, or a squared. Now taking this expression, we can see if we simplify, actually we don't have enough space, let's delete a bunch of this stuff and then simplify. Let's take this upward like this and say 1 over r equals this expression right here, and simplify it down. So taking this up, we can see on top we have rho times x times 10 to the minus 2, and also a rho times minus x times 10 to the minus 2. So these two would cancel out, leaving us with only rho times 20 pi times 10 to the minus 2 divided by a. So we'll have rho times 20 pi times 10 to the minus 2 divided by a, and for this part we'll have this divided by a squared going up as times a squared divided by rho times x times 10 to the minus 2 times rho times 20 pi minus x times 10 to the minus 2, which will be rho squared times, and if I take this x on the inside here, we can get 20 pi times x, 20 pi x minus x squared times the 10 to the minus 2 times 10 to the minus 2, or times 10 to the minus 4. So we get this expression right here, and we can see if we cancel out this a and a here, and this rho and rho here, we will get 20 pi times a times 10 to the minus 2 divided by 20 pi x minus x squared times 10 to the minus 4, and that's equal to 1 over the resistance R. So therefore, if 1 over R is equal to this, then R will be equal to reciprocal, which is equal to 20 pi times x minus x squared times 10 to the minus 4 divided by 20 pi a times 10 to the minus 2. Oh, actually I made a mistake here. I have missed the rho right here. So there's a rho right here, which means there's a rho right here, which means the numerator, there's also a rho right here. I've accidentally missed that. So anyway, with this we can see, we get this expression for r, which if I factorize out the x terms, we can see becomes rho times 10 to the minus 4 divided by 20 pi a times 10 to the minus 2 times the function of 20 pi x minus x squared. Now according to this, we can see our resistance R will be maximum when this quadratic function here becomes maximum. Now this quadratic function of 20 pi x minus x squared will be a function that looks like this, and in this function the two roots here are x equals 0 and x equals 20 pi. Now according to that, we can see right in the middle we will have the maximum term, which will have the x coordinate of the average of x equals 0 and x equals 20 pi, or x equals 20 pi plus 0 divided by 2, or x equals 10 pi. So therefore, the maximum resistance of R will be achieved when x is equal to 10 pi. So according to that, we can see if we take this expression of R and take it up, the maximum value of R in between a and b will be achieved when x is equal to 10 pi. So substituting in, we can see at that value of x equals 10 pi, we will get R being equal to rho, which now substituting is equal to 3 times 10 to the minus 4 ohm meters times 20 pi times 10 pi as x minus 10 pi squared times 10 to the minus 4, and the unit here is meters, divided by the 20 pi times the area A, which is equal to pi r squared, which over here, since we have 1 millimeter diameter, we have 0.5 millimeter or 5 times 10 to the minus 4 meter diameter or radius, and therefore we'll have pi r squared in terms of A, which is going to be equal to pi times 5 times 10 to the minus 4 whole thing squared meter squared times 10 to the minus 2. So this is the expression for the maximum value of R that we can get in this situation. Now simplifying, we can see we get R being equal to 3 times 10 to the minus 8 times 20 pi times 10 pi or 200 pi squared minus 100 pi squared or 100 pi squared, so times 100 pi squared divided by, and as denominator we have 20 pi times pi or 20 pi squared times 5 squared or 25, which I'm going to write as 5 squared, times 10 to the minus 4 squared or 10 to the minus 8 times 10 to the minus 2. Now simplifying, we can see 10 to the minus 8 and 10 to the minus 8 cancel, and we have 20 pi squared here and 100 pi squared here, which gives us 5. This 5 and this 5 cancel, leaving us with R being equal to 3 times, actually if we take this 10 to the power minus 2 upward, we can see we can have 10 to the plus 2 divided by 5. So that is the value of R. Now simplifying, we can see this is going to be 300 divided by 5 ohms or 60 ohms. And therefore, the maximum value of R is equal to 60 ohms. So the answer here is answer number 4 or 60 ohms. Now as a shortcut here, you can see we could have just gotten the point B being opposite to the point A. Now you can get that, and I highly recommend you get that rather than solving like this, because you can see by symmetry, if we have zero resistance at this point and zero resistance at this point, so when B is equal to, here we have zero resistance and here we have zero resistance, and as we go further we get higher resistances at the midpoint. By symmetry, we can conclude that we must have the higher resistance, and therefore we can conclude that when this length is equal to half of the diameter or 10 pi and this is also equal to 10 pi, we should have the maximum resistance. So that's a little shortcut here, but in this case you can see by hard coding and proving it, we found the same exact value of 60 ohms at the point where x is equal to 10 pi, which is the midpoint of the circumference right here. So anyway, the answer here is 60 ohms, and we are done with this question. Now moving on to question number 39. Question number 39 is actually incorrect due to a mistake in a single word. The question is supposed to say what is the maximum value of RB, but instead it says what is the minimum value of RB. Now for the purpose of this video, what I'm going to do is to cut out the wrong word and write the correct intended word of maximum, and then solve the question as intended to find the correct intended answer. So the question is supposed to say the transistor shown in the figure has a current gain beta of 20, has VB equals 0.5 volts and VCE at saturation of 0 volts, and given this, the question is asking us what is the maximum value of RB needed for the transistor to operate in saturation mode. Now looking at the diagram, we can see we have a transistor here where the emitter is directly connected to the ground, the base is connected through RB into 6 volt source, and the collector is connected through a 120 ohm resistor into 12 volt source. Now if the transistor here is operating under saturation, then we can see VCE should be equal to 0, and therefore the voltage from this point to this point is equal to 0 volts. Now considering that since E is grounded, we can say the voltage at C will also be equal to 0 volts, and therefore across this 120 ohm resistor we have 12 minus 0 or 12 volts being applied. Now according to that, if we apply V equals IR, we can see we'll get I equals V divided by R, which is 12 volts divided by 120 ohms, which is equal to 0.1 amperes. So therefore the current here going through this resistor and through the collector is equal to 0.1 amperes. So we can say IC equals 0.1 amperes. Now at this point, if we stop for a moment and consider the behavior of IC and IB, we can see initially as we increase IB, IC will increase linearly like this under the relationship IC equals beta IB. However, at a certain point, IC will saturate and become a flat line related to IB like this. So we will get a curve that looks like this. Now at this point, the current here is equal to the saturation current of 0.1 amperes. So the current here is 0.1 amperes. Now I want to draw your attention to this specific point right here. At this point, we are both on the curve IC equals beta IB and on the flat line IC equals 0.1 amperes. So therefore, IC is equal to 0.1, but we still have the relationship IC equals beta times IB, or 20 times IB. Now at this point we can see if we divide both sides by 20, we get IB equals 0.1 amperes divided by 20, or 0.005 amperes. And therefore, at this point the base current here IB is equal to 0.005 amperes. Now it should be noted, this base current here is the minimum base current for which we are under saturation. For all higher base currents we are under saturation, but this current right here is the minimum current under which we are under saturation. Now looking at the question, we are asked to find the maximum value of RB under which we are under saturation. And as we increase RB, we can see IB, this current, will reduce. So due to that, to get the maximum value of RB under saturation, we need to find the minimum value of IB under saturation, which is equal to 0.005 amperes. Therefore, if we have the maximum value of RB here, then the base current here is equal to 0.005 amperes. Now under that we can see VBE is given to be 0.5 amperes, and therefore the voltage drop here is 0.5, and we have 6 volts here, and therefore the voltage difference over RB here is equal to 6 volts minus 0.5 volts, or 5.5 volts. Now according to that we can see, if we have 5.5 volts across RB, we can apply V equals IR and get R equals V over I, which is equal to 5.5 volts divided by 0.005 amperes, which is going to be equal, dividing the 5, we get 1.1 on top and 1 over 1000 on the bottom, which gives us 1100 ohms, or equal to 1.1 kilo ohms. So therefore, the intended answer here is answer number 5 of 1.1 kilo ohms. However, you will probably get marks for all answers because here it says minimum instead of maximum. So with that, we're done with question number 39. Now finally, if you go to question 40, it says, in a photoelectric experimental setup, the cathode is illuminated by a light source and the frequency f of the incident light is increased while keeping the intensity of the light beam constant. Now given this, they ask us, which of the following graphs best represent the variation of the photocurrent I with the frequency f? Now here, as we increase frequency, since we keep the intensity constant, i.e. the number of photons per second constant, the number of electrons per second, i.e. the current, must also be constant as we increase frequency. So therefore, answers 2, 3 and 5 are all wrong, since in each of them, as we increase frequency, the current also increases. Now consider the other two remaining answers. You can see in answer number 1, we have a constant current, but it only starts at a certain minimum frequency. In the fourth one, however, we have a constant current that starts at f equals 0. Now in the photoelectric effect, we know the equation work function phi equals h times f0, where h is the Planck constant and f0 is the minimum frequency of light required for the photoelectric effect to work. At the frequency f0, the photons have the exact amount of energy needed to break an electron out of its orbit and release it into the wild. Now according to that, we can see if we have any frequencies less than f0, then there will be no current in our material, and therefore answer 1 is the correct answer because in it, at frequencies below f0, there is 0 current. So answer number 4 is wrong, answer number 1 is correct, and we are done with the questions from question 31 up to question 40. So I hope you enjoyed. If you have any feedback or questions, post in the comments down below. Thank you for watching and goodbye.